All right, so let's get started. My name's Derek Chu. I work at Microsoft. I lead a team that provides the platform for FPGAs in our data centers. I'm going to be talking about how we actually use FPGAs to differentiate our data center, enabling us to customize the same hardware for a variety of different applications. So we look at today's data centers. They're very big these days. Order 100,000 servers per data center. They're tens of megawatts. Very, very strict power and cooling requirements, and they're incrementally upgraded over 3 years. So if I wanted to go and deploy a new piece of hardware, there's no way I could get it deployed even within 3 years across the entire data center, because there will still be old servers from the past. So it becomes very, very difficult to go and do a mass upgrade. So improving efficiency in any way has very, very high impact within a data center. So if we look at efficiency versus specialization, this is the standard graph that people are used to. If we're more flexible means that basically microprocessors are going to be more flexible. They allow us to program, and they allow us to do that very quickly, but they're not very efficient. Right? Overall, the energy efficiency of executing an instruction is very low because there's so many transistors that are actually doing nothing. They're not doing the actual operation themselves. They're doing a bunch of bookkeeping and overhead and maintenance in order to be able to get those instructions to execute. On the other hand, just pure, straight, dedicated hardware on the right will give you very, very high efficiencies, but they're very difficult to program. So we basically looking at, we're obviously going to have microprocessors in our data center servers. We're looking at different ways to specialize, and we looked at ASICs, FPGAs, and GPUs as possible ways to accelerate and to specialize. So we can by applying this kind of hardware, we kind of deal with the fact that Dennard scaling is ended and the slowing down of Moore's law. Right? Fundamentally, if we don't do some hardware acceleration, we don't provide some additional specialization, we'll stay at the same efficiency of the microprocessors, and that means our efficiency improvements are slowing down over time. So what we're looking for is really a single platform that supports a wide spectrum of use cases. So looking at the GPUs, ASICs, and FPGAs, if we look at each one of them individually, the GPUs are not fully general. It's hard to do networking, for example, on a GPU. It's great for doing things like machine learning. They tend to be very power hungry, and they tend to be very costly. They're very big FPGAs, as Mark mentioned earlier. The current versions, they have smaller versions, but the current big version that's got the most capability is 800 plus square millimeters and 300 watts. ASIC is really specialization versus generality. If I want to specialize very highly, I can make a very, very efficient ASIC, but then that's going to lose all the generality I want. So it's going to be very hard for me to make a single ASIC that's going to be applicable across the board to various kinds of applications and infrastructure that we run in our data center. And there's, of course, it takes time, and there's high engineering costs. So we selected FPGAs. So if we look at FPGAs in a little more detail, the pros are you can actually have a very highly specialized function versus a programmable engine. Most people think ASICs are highly specialized, but in reality, if you look at what an ASIC actually does most of the time, is there are actually configurable programmable engines inside. For example, if I want to have a crypto engine inside of my ASIC or inside of my microprocessor, inside of my data center server, I don't necessarily want to dedicate it to be AES GCM 128. I might need 256. I might need CBC or XTS. Right? So I can't go and say I'm going to use a single, very highly optimal, very efficient ASIC engine that just does one crypto standard. Most of the time, I'm going to build an ASIC that allows me to do a variety of different crypto standards. And that actually starts adding in some inefficiencies, because either I have multiple paths that each one of them do a single version of the crypto standard, or they have a little microcoded engine or a little processor that will allow you to implement many different standards. An FPGA, on the other hand, is because I can go and change it in the future, I can go and implement a single standard for today. And if I need to change it for tomorrow, I can do that tomorrow. FPGAs are weeks or months worth of iteration time. I define some function, I can potentially implement it in a few months. If I need to iterate on it, I need to fix a bug, that could be weeks or even shorter. So this allows me to go and adapt very quickly to my changing needs and to development effort. I can do deferred engineering here. I can do a less than perfect implementation today, and I can go and refine it over time and make it better. Right? This is a really nice way to do engineering that allows me to go and get some real data back from the data center and discover what I really need and then go and refine it as I need to and expend the engineering effort when I need to. And they're actually more efficient than generally thought. A lot of the FPGA these days is hard blocks, very, very efficient blocks like very, very efficient dual-ported memories, very efficient DSPs, very efficient PCIe controllers, DRAM controllers, memory controllers, and so on. The cons are, of course, they're suboptimal for any specific circuit. Obviously, if I know I only need AES-GCM128, an ASIC block will be more efficient, and they have higher power. They consume more power. So where would I place my FPGA for kind of maximum differentiation inside my data center server? This is what we decided to do. What we're doing is we're putting the FPGA right here. So this position, here's a standard dual socket processor. This is 2 CPUs. Let's say they're Xeons. We've got a NIC attached across PCIe. But every single packet that goes in and out of this server goes through the FPGA. Right? So this actually gives us a tremendous amount of power. It allows us to observe every single packet that goes in and out of the server. It allows us to process every packet that goes in and out of servers. It also forces us to process every packet in and out of server, at least passing it through. So there's some additional responsibilities that come with this position. We also have a standard PCIe connection, which allows us to act as a standard compute accelerator as we're talking to the server. So fundamentally, in this position, the FPGA offers us a wide range of possible acceleration opportunities. For instance, it could act as a local remote compute accelerator locally here, or I can have some other server go and ask this FPGA for to do some computation and return the result. Or I can do kind of networking and storage accelerators through this network path and along through this PCIe path. So I can do both infrastructure and compute acceleration. Now, just to make this point perfectly clear about the connectivity, each one of these FPGAs, is the main connection to the TOR. Right now, we're deploying 40, 50 gigabit, and this TOR allows us to communicate across the data center, in fact, even across the WAN if we so desire. So it's got a lot of scalability. So how should we think about our data center server? And this really depends on your point of view, and everyone's point of view is different. So if we look at a standard map of the world, and when I say standard, this is the US and European maps. I actually went and tried to find European maps for these next few slides, and it turns out, as far as I could see, European maps look very similar to this one. Europe is in the center of this map, the US is off to the left, and because we normally view from the left to the right, this is the center of the world. So what do you think a Chinese map looks like? Well, looking at a Chinese map, that's China right there. You see, kind of China's here, Europe is kind of off here in the corner, and the US is off to the right. The center of the world, even though it's the same world that we all know and love, the way we view the world is different based on our point of view. So these, I actually went and I did look for various maps, European maps, and it turns out Europeans are not as nice to each other. So I was looking at some of the maps, I'm like, I can't put this up in a public presentation. But so I went and stuck with the US ones. I'm sure that everyone knows these stereotypes. I'm from Texas. Austin is the center of the United States. They're damn Yankee land up here, uninhabitable California, and so on, and basically swampland down here, right? So if you look at the same US, Texans have a very specific view. The US, the center of the US is Texas, and everything else is not as good, all right? If we look at how Californians see the United States, California is awesome, single word. Coffee comes from Seattle. Texas is actually fake cowboys and pickup trucks, and they're a bunch of religious nutballs who try to force their religion on us here in the kind of Midwest, I guess. All right, so again, the same US, but very, very different points of view. So let's take a look at our servers. So if we look at the computers over the evolution of time, because CPUs were really designed to minimize the number of transistors and to maximize the use of those transistors, everything was shared, and the CPU would do everything from doing the basic computation to loading the program to taking interrupts to dealing with I/O and so on. Everything is done by that same central processing unit. And that's part of the name, it's C, the C is central. Right, so as time went on, it was pretty clear that the CPU couldn't handle everything. And so what we wound up doing is building in various accelerators that could then help that CPU do what it needed to do. So there were NIC accelerators, you may have GPU accelerators, FPGA accelerators, and so on. But the accelerators are always viewed as an offload engine for the CPU. right? It wasn't the main, it wasn't the main computation. The CPU was the one who got to decide what got offloaded. Now, networking is a bit of an unusual case, but even then it was considered an offload engine rather than something that was in command of the server itself. All right, so here's another view of a data center server. We can really view the FPGA as the center. This is exactly the same architecture as this picture, but we go and redraw it the way Texans might draw their map or Californians might draw their map. The FPGA in this particular picture kind of shows off where its position, which is in the front of every network packet that goes in and out of the server. CPUs are kind of off to the side because they are all the packets that arrive to the server that need to go to the CPU have to first go through the FPGA, and the FPGA has to decide to send each and every packet to the CPU. Now, most of the time, 99% of the time, or even much more than that, the packets go to the CPU, but the FPGA is sitting there in the front. So what are the benefits? You can map common case work to the FPGA. What this means is if I need to do things, if I need to process every single packet in some way, like we have to for software-defined networking, the FPGA can do that. And in the case where the FPGA knows what to do, it doesn't even have to bother the CPU at all. The CPU is off, relaxing, doing whatever it does. It's doing, the FPGA is handling the per-packet workload in the software-defined networking world. And of course, the processor can read and write system memory as is needed in order to keep state to maintain consistency, coherency with the CPU system, right? So this allows us to do this kind of activity. So in reality, if we view what the CPU is now, the CPU is actually a complexity offload engine for the FPGA. CPUs are great at dealing with gigabyte executables because they have virtual memory, they have caches, they're able to move stuff around. FPGAs are not good with that. And one of the reasons why FPGAs are fast is because I go and load the program and I don't try to change it while it's running. Taking an instruction cache miss or even a page fault on an instruction is a huge amount of bubbles in your pipeline. And these are bubbles you can't get back. So fundamentally, by mapping the appropriate code into the FPGA and not changing it on a per-packet basis, you get a huge performance win. Right? And that allows us to have the high performance, and we let the CPU go and deal with these these uncommon cases, but ones that require potentially more resources, or at least more virtual resources. Right? So in this particular architecture, we have many different possibilities. I'm going to be talking about distributed machine learning and software-defined networking as the two cases that we've been publishing about from within Microsoft. All right, so let's take a first look at DNN inference acceleration. So this is a project called Project Brainwave. This was actually presented in Hot Chips 2017. I'm just borrowing their slides. But this is a scalable FPGA-powered DNN serving platform. So it's very fast. It's ultra-low latency. This was actually designed to be very, very low latency because it was originally designed for Bing. And for Bing, latency matters a lot. They want batch size of 1, and they want the minimum latency with batch size of 1. So why is that? Well, when a query first comes into the server, if I had a batch size of 64, that means I've got to wait for 63 other queries to come before I can start processing the first one. And if latency matters, it's like having an UberX, which will take me, as soon as I want that Uber, it'll come pick me up, as opposed to waiting for the bus. Right? The bus may be more efficient, but the Uber is going to get me there much faster. The latency is going to be lower. So fundamentally, we targeted Brainwave for ultra-low latency and very, very high throughput because Bing requires a lot of throughput because we're processing each and every one of the queries in this way. Flexible, it's adaptive, numerical precision, and custom operators. What this means is I can go and actually, rather than having to use 32-bit floats or 16-bit floats or 16-bit ints, I can actually shrink down my numerical representation. And my FPGA allows me to do this in a very efficient way. So by doing that, I can actually pack much more computation into this FPGA than I would be able to get from a static ASIC, which will have predefined data types that I cannot change, right? And it's friendly turnkey development on CNT, Caffe, and TensorFlow, and so on. The intention is we go and take your model and automatically compile it into this system. So essentially, we're taking these DNNs, we're mapping it across multiple FPGAs, and we're having on each FPGA, we have this specialized processing unit. All right, so if we look at the way we traditionally do DNNs, this is the local offloading and streaming, and we're looking at kind of a CNN-like computation where the amount of computation is very high, relative to the amount of the weights that we're using. So what winds up happening is we'll put our model, at least the model parameters, they're put in DRAM. And what will happen is okay, the animation didn't work. But what will happen is that the query will come in, the FPGA will go and basically call the DRAM and cycle through all of these model parameters. What this means is fundamentally this DRAM to FPGA or DRAM to accelerator bandwidth is going to fundamentally limit the performance of my system because I'm relying on the fact that I'm putting more models that fit on the chip into the DRAM and kind of shuffling them in as they're needed to do the computation. Instead, our approach is using persistent neural networks. And what this is really doing is it's saying and locking those weights down into the FPGA fabric. In fact, Mark talked about this. Other ASICs are doing this as well these days. But state-of-the-art FPGAs have order 10K distributed block memories, each one of them about 20 to 40K bits big. And so we have order 10 megabytes of state, actually considerably more than 10, kind of in the 30 to 40 to 50 megabyte range. So you can actually pack a lot of parameters onto a modern FPGA. We have tens of terabytes of second memory bandwidth. In fact, on the Stratix 10 that I'm going to show you some results for, the memory bandwidth is about 140 terabytes a second. This is against SRAM, of course, not against DRAM. These kinds of parts also have HBM memories and so on, so they also have high bandwidth DRAM as well. So what winds up happening here is we go and map these weights into the FPGA memory, and now we don't have to go out to the DRAM and access. So we can, what we now do is as a query comes in the door, or as a inference request comes in the door, we use the entire FPGA using all of the resources on the FPGA operating in parallel to execute that one specific query, rather than we parallelize across the chip for one query, rather than trying to parallelize across multiple queries and using the DRAM to do that. All right. So what happens if your model doesn't fit in a single FPGA? Well, it's pretty simple. What we do is we now go and map that model across multiple FPGAs, and we send messages. We actually send, we send the information between the layers, between FPGAs, to go to the next layer that's evaluated in the next FPGA. Of course, we can partition this in many ways, but that's a partitioning that actually reduces the amount of memory bandwidth or amount of inter-FPGA bandwidth that's needed. So fundamentally, because all of these FPGAs are connected directly to that 40 gigabit or 50 gigabit or 100 gigabit per second network, we can actually move a lot of data very, very quickly. And we can get this computation done at very, very low latencies. So let's go and take a look at the performance numbers that we get. So if we look at, this is a Stratix 5. This is a 2011 FPGA, 28 nanometer. This is very, very old technology. So when we first started using 16-bit integers, and we got about 1.4 teraops per second, which is actually very, very respectable. But as we went and tuned these particular data types, we got more and more performance, to the point where we, in this particular, at this particular snapshot in time, we're using a Microsoft floating point 8. This is our own floating point 8 representation, and we're getting 4.5 teraflops per second on a 2011 part. That's in a lot of basically all of our data center servers after 2015. So that's a huge amount of performance if you're considering batch size of 1. It's small compared to people's numbers when they're talking about batch size of 64 or 128. But for batch size of 1, this actually beats pretty much all the published results that we've seen for this time frame. Now, if we go and look at the Stratix 10, which is a significantly better part, this is a part that's current today, that's available today. The same data type is 90 teraflops per second, and this really is world-class. Nobody has numbers that are comparable to this at batch size of 1 today. So the other, I also want to say that I don't have these in the graph, but as we go between these different data types, you actually see no degradation in inference accuracy. Right? Fundamentally, the models have been retrained so that they will now go and run just as well on the 8-bit as they do on a 16-bit, and even a 32-bit float. They're all equivalent. All right, so now let's move on to software-defined networking acceleration. So we're using exactly the same server and exactly the same server configuration, and we're doing network acceleration on the same system. All right, so this is the FPGA SmartNIC for Cloud Networking project. Basically, Azure runs software-defined networking on the host. right? So what that means is if you're a customer and you want to bring your own IP address, let's say you've got a 10.1 IP address, that's your internal local IP addresses that you use in your own data centers, and you want to be renting Azure servers and going and essentially making that Azure server look like an internal local data center server. What you want to do is you want to have the same IP address, right? And you want to be in the same IP space. And so you might want to send that 10.1 request out to you, and that's going to go to one of the Azure data center servers, and then we need to be able to return a response using that 10.1 IP address as well. Now, the issue here, of course, is 10.1 doesn't mean anything inside the data center, right? In fact, there's going to be many, many other companies and servers that may have the same IP address. So on each host, what we do is we go and do a lookup of each one of the packets that goes through, determine what flow it belongs to, and then determine a set of rewriting rules which may actually go and encapsulate that packet or decapsulate that packet based on the rules, based on the VM that you're coming from and the destination you're going to or coming from. All right, so this is actually quite a bit of work, which was traditionally done in software, but was very slow. Before the SmartNIC project, we relied on ASICs to scale and be COGS competitive at 40 gigabit per second. But the 12 to 18-month ASIC cycle time plus the time to roll out new hardware was too slow to keep up with software-defined networking. And as we grew our network bandwidth, the number of cores we were using to go and do this processing just kept on growing as well. We're actually losing a significant number of cores to do this work at 40 gigabit per second and above. So SmartNIC gives us the agility of software-defined networking with the speed and COGS of hardware. So the intention is we'll go and implement particular components. In this case, for software-defined networking, we have this thing called generic flow table, which basically goes and lets the hypervisor essentially go and load these rules, these flows and rules that allow us to process each one of the packets. And then that implemented on the FPGA will go and do the processing and do the appropriate thing. Obviously, the first packet that goes through, you have to go back to software and ask what to do about it. But every packet after that, we're able to process through the FPGA. So if we look at a little more detail of what that actually does, now in the previous world, what we would do is we'd have this stack where the VM would go and run on the guest OS, which would run on top of a hypervisor, which would run on top of the virtual filter platform, which is the software version of the software-defined networking, which to run on top of the NIC. So in each one of these cases, there's a transition from, you can think of user mode to an operating system to another operating system down to, this one is VFP runs on the hypervisor, but in some sense, you have to transition between each one of these stacks. What we now enable is we turn on SRLV onto the NIC. This was not possible before because if the VM was allowed to talk directly to the NIC, we don't know what kind of damage it could do, who it could send to, what kind of denial of service attacks it could create. So now what we do is, in this new world, we do let the VM talk directly to the NIC, but every packet that goes in and out of the server now goes through the GFT block on the FPGA, and it's rewritten appropriately so that the address is correct and is allowed, right? So we also can detect if someone's trying to spam someone else or DOS them, we can go and eliminate those packets because we know that that particular VM is not allowed to talk to anyone, to someone that they might be having ill intent. Every VM is only allowed to talk to the other VMs that they're allowed to talk to. So by having the FPGA determine all of this, things go much faster. It reduces the latency down to roughly bare metal. So you're running in our cloud, you're actually getting the performance as if you're running in your own data center network, right? Your own data center. Azure now has the fastest public cloud network, roughly 30 gigabit per second at 25 microsecond latency. So in conclusion, by plugging these FPGAs in the position that we plug them into and programming them correctly, we have a single platform that both gives us top-class performance for our customers like Bing running on these kinds of servers, for machine learning and obviously others, and also for the main bread and butter Azure work, infrastructure work such as networking. We have best-in-class DNNs, we have best-in-class networking, and we have other components coming as well. And I think it's important to note the wide range of capabilities. We're doing DNNs and networking on the same part, and this is on an old 2011 FPGA because that's what we've deployed most of. We're deploying newer FPGAs, which will give us more capabilities, but these capabilities that you're seeing are based on 2011 FPGAs. There's incremental effort to deliver the next capability, and we can reconfigure deployed servers with code that wasn't even conceived of at deployment. there actually were cases where we deployed something which we didn't even think we would be able to do when we first bought the hardware. And now we're going and deploying these new kinds of capabilities on hardware that's already deployed in the data center. Right? This gives us a huge amount of power. All right. Thank you.